Alright, welcome to another video. So we're going to start on a new use case today. This is use case 6, so we're moving right along. We're almost 2/3 of the way done with the book, so it's amazing how much progress you can make when you just chip away at something over time. So use case 6 is, what are the driving factors for problems in my network? And I'll do an audio check. Audio looks good. Pain point. This is one of the use cases that I like the most because I find it really fascinating how certain techniques can be used in such a broad spectrum of use cases. From recommendation system for purchases to solve such a fundamental pain point in large network and cloud infrastructures. In every network and cloud infrastructure, the larger it is, the more heterogeneity there is in terms of devices, hardware revisions, software versions, configurations, operational conditions, environmental conditions, and probably other factors. So I'm not sure what's meant by heterogeneity. Oh. Okay, so see, I thought, hetero. Yeah, so what this means is the quality or state of being diverse in character or content. For some reason, I kind of thought the author was saying that they are more the same the larger it gets, but no, it's the opposite of that. Those factors influence in one way or another how the network as a whole operates. We have all seen how certain combinations of the above factors result in malignancy for the network and cause problems. However, the challenge is identifying those combinations. Is it a specific software release? Is it a particular hardware revision or component? Is it a certain configuration? Is it a combination of them? If so, which combination and how many? It is very difficult to identify at a first sight what is driving problems in your network and what is potentially driving problems disproportionately based on the footprint such factors have in your infrastructure. Some of these factors may be contributing to 10% or 5% of your network issues. If you can identify those factors, then you can act on them. Maybe change a software release or avoid a particular combination of software release and hardware revision. But if you do not know about them, they are like the famous needle in the haystack. You have a large infrastructure and you want to put in place mechanisms to improve your network or cloud SLAs. However, you cannot identify what are the factors that are driving these problems. Then what can you do to improve? Therefore, the pain point that we will address in this use case is precisely to identify those harmful combinations of factors that are contributing negatively to the performance of your infrastructure. Approach. Let's imagine a shopping basket in a certain supermarket, online or physical. Every transaction is a combination of items people purchase together. Supermarkets are very interested in finding what those frequent combinations are, frequent patterns of purchase. Likewise, they want to find the association rules of specific combinations with particular items so that they can plan commercial strategies, bundles, special pricing, among others. This is a very well-known and established practice, and it is behind the recommendation systems from major retail companies. In IT and other fields, the same type of algorithms have been used to identify frequent patterns associated to failures. Let's explain the analogy here. Instead of a purchasing transaction, let's imagine that our entity to track is a network failure. In our example, we will use a hardware failure event as the tracking entity. When such an event happens, there are certain properties associated with that event: device vendor, hardware revision, software version. There could be many. We will select some in our exercise. We can, therefore, use the same algorithms originally used in recommendation systems to find out what the frequent combinations of those factors are among the different hardware failure events. In your network and cloud infrastructure, you may already be doing a top N for this, but the top N may give you a bit of a misleading view. The software release associated with more hardware failures will likely be the most deployed software release on your network. That's a good point. So let's say you want to say like, which device, Cisco, Juniper, or Extreme is more reliable. Oh, well, look, we have all these Cisco failures. Yeah, well, 99% of your network is Cisco. Of course, they're going to be the ones that fail the most. So, yeah, it's all about the data and garbage in, garbage out. You have to the quality of your insights depends completely on the quality of your data. So you almost have to be kind of a data engineer and data scientist first if you really want to be a good machine learning engineer. All right, so it is not just about finding out the combinations, but also finding the probability. Oh, and he's got that error. I'm not going to alert him at this. I've alerted him twice. I feel like I just kind of serve to embarrass him when I do that now. He's going to go through and fix the other ones, he said, so I'm sure he'll go through the rest of the book and look for it. So it is not just about finding out the combinations, but also finding the probability of these combinations so we can properly assess the result. Mathematically speaking, this is what we want to find. Okay, so really important to understand here. This is just a complete typo. There's, it might as well say PFALURE. There might as well be a spelling error here. Or like combination could be spelled COMNBINA. This is as much of a typo as a misspelling of a word would be. It's not a small thing. It's the incorrect operator. So the way probability mathematical notation works is you have this capital P, and then you have parentheses, and then you have the left side of the parentheses, which is specified with a pipe, not a forward slash. And then you have the right side of the parentheses specified that way. I feel like a comma could probably be better because then you're less likely to make this error, because this is a pretty big error. But that's really important to understand because this is not a division operator. And if you don't know that this is a typo, you could get very confused and think, oh, well, you have to divide the failure by the combination to get probability. But no, it's not an operator at all. What it's saying is the probability of some combination of X leading to. So in fact, not only is this not a division operator, it's completely unrelated to division at all. It's not even in the same category as division. It means leading to. So the probability of combination X leading to a failure times the probability of a failure divided by the probability of combination X equals the probability of failure being a result of combination X. A specific combination X that results in a high probability of failure, conditional probability, is a harmful combination. Based on the chain rule, and Bayes' theorem, we can obtain such conditional probability. So I think the chain rule in this context does mean the same as it means when you're learning basic calculus. So it is important to have some, this would be considered, I would probably consider this advanced mathematics, but honestly, it's not. Like, what you learned in school was really dumbed down, appealing to kind of the lowest common denominator. So like, if you have a career in tech, just spend, and you're not super confident with mathematics. I mean, I'm not. I feel like I'm not up to speed with math the way I'd like to be. But a really good source is Khan Academy for the basics. Then beyond that, like actual Udemy courses. There's also like online courses. So like massive like online courses for mathematics. Yeah, so you can get certifications like Coursera, edX. Those are good ones. I would say probably the best thing you can do is just buy a textbook and read the textbook. Like, honestly, just do that. And I might even think about doing something like that on this channel, because that would be a great way to learn. So we just say, because once you're learning the math, like, it may be over your head, it may be hard to follow along, it may be boring, but you're really getting to the crux of the issue. Like, you're learning the meat and potatoes. You're learning like what actually matters to know. Like, anything else is just going to be a proxy for learning the math, or like, some secondhand source. Like, you're diving into the primary source. So if I search for mathematics textbook, there we go. We've got all sorts of. So here's the calculus textbook. You can probably even get it. Yep. So you can get it on a Kindle, and I could read it on the channel. And it's part of a whole series of textbooks, the Dover books on mathematics. I really think this is probably one of the best ways to learn mathematics. Because forget about even Khan Academy, like, Brilliant, all these things. Like, they're just gonna advertise to you. They're just gonna try to get you to sign up for a subscription. They're gonna bother you. They're gonna show you pop-ups. They're gonna have you accept cookies. It's like, forget about it. You got to deeply focus and think about the task at hand. Like, notice how I don't get any pop-ups or cookies or requests to update with this application. Like, it's essential that you don't get hassles while you're trying to learn something complicated. So this is what I would recommend most, is get a textbook and read the textbook. And a lot of people are like, oh, well, you can only use paper books. And I was kind of like that, but I've kind of changed to be like, it doesn't even matter, even if it's an ebook or even if it's like an audiobook. Like, it's kind of like for muscle development and weightlifting, the main factor, and this I'm getting off track here, so this is if this video I mean, but from what I understand, time under tension is like the only factor that really matters. So I think it's the same for like learning mathematics. It's like time under tension of like thinking deeply about mathematics is like the only thing that really matters. So you got to try to maximize that time. All right. So got sidetracked there. We can obtain, so based on the chain rule and Bayes' theorem, we can obtain such conditional probability. The generic P probability of failure, is not differential to each combination. So we can ignore that element in the equation. We are more interested in having a relative view on what combinations produce failures compared to other combinations of factors. Therefore, we need to obtain the conditional probability of a certain combination X, given that there has been a failure. The purchasing basket recommendation algorithm above will provide that. And we need to compute the probability of a certain combination X because we have the full network inventory, we can compute such probability. So at the end of this exercise, we should be able, with the methodologies described, to surface which are the factor combinations that result more harmful in your network. As a consequence, this will enable you to act on them so you can eliminate their contribution and progressively improve the performance of your work. The approach described in this case is based on existing public research. Oh, that's cool. See 32 for reference. So I'm gonna advance the bar and look at that. So the next section is input data. So I'll advance it here. I do have to say, I think this is something you could probably do at your job. Like this would be a great thing. Like all you do is you identify the combinations of factors that result in harm in your network. So like one of the factors would obviously probably be some bozos logged in, like a show users command constantly shows the same guy wreaking havoc, and you know it's the same thing because you know, as I said, like, oh, is it Cisco Juniper Extreme that is causing issues? Well, it's Cisco because 99% of your network is Cisco. Okay, it's that one guy logged in because you know they're on the night team and they're doing all the work, and you know it's. So you no matter what you apply the methodology to, you still need to adhere to those best practices to make sure that your data is high quality enough to give you actual meaningful results. So before going on, I do want to skip to this reference and look at it quick. So the Annex A. Oh, here's the recommended bibliography. Yeah, so this is where it's referencing. So number 32 was the reference. All right, so we can see this is actually a oh, was it 32 or was it 33? Oh, it's 32. Well, it looks like 33 is a better hit. And there's no, yeah, that's definitely the correct section. Nothing else is labeled the same way. Yeah, so it's definitely 32. It does look like 33 is a better hit though. Real-time statistical log anomaly detection. But anyways, let's look at 32. Okay, so now we've got this paper here. We can see it's a paper that is oh sweet, that is free and accessible online. That's good. I like that. And we can see the abstract. Which let's just jump down to the conclusion. I don't know how to read papers. Oh man, yeah, papers are hard to read. Yeah, there's just a lot, so that's okay. That's what. And notice how there's no forward slash there. There's a forward slash there because it's meant to be a forward slash. But anyway, that's why we're reading this book. So you don't have to read the paper. One of the capabilities of SANS is to generate events, structured events, as well as syslog messages, unstructured events, based on templates that are defined. We are going to run our use case by analyzing what is influencing the existence of hardware errors. In this case, they are represented by devices sending a specific structured event that we will categorize as warning hardware fault. You could use for your network other types of events or specific alerts that you have configured in your network or specific syslog messages that are concerning. In SANS, there are two mechanisms to generate event data. One, via event policies, where we can specify what events need to be generated for a certain device or interface, the cadence, and the probability. This is how the event policy table looks like, and it is fully configurable. Each entry defines what type of event needs to be generated. Event ID defined in the event templates table. What is the periodicity? Periodicity, right? Oops. So I have to delete this note now, which is going to be impossible to do. So the note is still there. Let's try doing notes. Okay, the note is not still there. Great. And then we'll filter out for bookmarks again. There we go. So now let's try to get a pronunciation for this word.
Periodicity.
Periodicity. Okay. What is the periodicity? Every minute, hour, day, week, month. What is the probability that the event is generated? Which entity the event should be associated to? And the specific fields that are required to generate such an event. With this, we can control the frequency and probability of different types of events and simulate different types of situations, hardware faults, software bugs, restarts, etc. Alright, so now we're diving into the actual Jupyter Notebook. So let's try to get this event policy object to display. Alright, so I've got one port here that's still live. I don't think it's still active. No, it would load up to it right away. So it's a dead port, and we can see here it's a dead port. So let's get rid of it. Alright, and now we're at there. So this is use case 6, but we'll just open Jupyter from here. Alright, let me get that pop up. Okay, so use case 6, toxic combinations finder. Perfect. All right, so we're installing some modules. One thing we learned is that in order for them to be installed so that they're usable by Jupyter Notebook in the running kernel, you have to use a % rather than an exclamation point. The other thing we've been doing is running it locally, so we don't need the statement there. And then we do need to change the next cell, and then we need to be extra careful to change it to use case 6. All right, and then we need to change the import statement for SANS. All right, looks good to me. So then this is the cell we're going to try to get down to. Oh, so forgot one line here. Import sys. All right, so we'll get this events underscore df to print. Number 2, via incident policies, An incident is a construct in SANS that allows us to combine various types of changes synchronously so we can simulate how a burst of events or changes in metrics, would happen simultaneously or in a certain sequence should such type of event happen. The following table is the incident policy table. These tables are defined in SANS. See Annex A for details on how to construct them. Okay, so next is the table there. So we're still working on this. The index destructor will not infer. Okay, so there's a problem with pandas. I guess the version being used must be pretty far out of date. But anyways, we're using this here. We should get to the concat warning. I did save the changes where I changed it from append to concat, but just for one section of the code, I did not change because the data appending to the data frame is more complicated to figure out what that actually is. It's not just clearly statically defined right beforehand. So this might take a while, so let's get some reading done in the meantime. In our case, we are going to use the event policy approach. We want to force certain bad behavior in some types of devices in the network. This bad behavior will cause those devices to generate an abnormally high number of hardware error events. See how the event policy looks like. Okay. There are a number of policies defined that will make some devices generate error messages with a low probability, 20%. Other devices will generate them with a somewhat medium probability, 40%. Other set of devices will generate them with a very high probability, 90%, and the remaining will have a very low probability to generate error messages, 15%. Given this, we will run SANS to generate the events we need. Obviously, we are forcing things to happen, and the periodicity, minute, may not be realistic, but I want to concentrate on a short period of time, a larger number of events, so we can apply analytics. It takes a while to generate all these events for the 10 days period. So, like in other cases, there is a pre-generated file that contains a sample of the events, so you can load the CSV file directly if you prefer. And the file is Events Toxicity Analysis, CSV. So we're going to get to this data frame now, events DF, so hopefully we can get there. Let's check back in on the notebook. So still working with this. We have a warning here saying that in a future version. So, but it should be fine for now. All right. So we're not going to be using the existing file. So I think this yeah. So I think this file we need to get rid of this cell here. So I wonder if I can comment it out. Since it hasn't run yet, I'm hoping that I can make changes to the cell and then it will run including those changes and not when I clicked run, whatever was in there. All right, so that's still going. This is how the event table will look like, how the event table looks like. So we got some warnings here. Then we've got a list of dictionaries, key value pairs. I don't know if there's more than one dictionary. There are more than one key value pairs in this dictionary. But this should look pretty familiar from the last few videos. This looks like it's able to be converted into a pandas data frame. All right, so I'm going to advance the bookmark, and I will take a bit of a break here, a few minutes break, and hopefully when I'm back, this will be done. But if it's not, I'll keep reading when I come back. All right, I'm back. We're at the half-hour mark. Usually do an hour pretty easily. Let's check back in on the notebook. And the notebook is still working. I have no idea how long it's going to take. That's too bad. All right, well, anyways, on with the reading. In our case, the timestamps will not be useful for this analysis, nor the event name, because in this case, it is the same for all. We will focus on which device generated the event, source, and its attributes, fields. Note, though, that in your case, you may have an alert or log collection system that receives the messages, so you may have the source but not the attributes, vendor, model, version, hardware, revision. The latter is data that is in your inventory. You may need to collect that information, load it in your Python notebook, and merge the two tables so you can enrich your event table with attributes for the device that generated such events. We have more than 27,000 events to do analytics with across all the PE devices in the network. Likewise, one important data source for this use case is the inventory. SANS has a function to generate the device inventory table, which we will use as well. Since it is very fast to generate, we do not have a CSV file in this case. You should simply run the command in the notebook. All right, so to get the inventory DF, you can generate it, and it shouldn't take as long as this command here. And this isn't even the command, interestingly enough, where there's a oh no, it is because it is. This is the command you can skip and load a file in for. So you would comment out this. You would comment out this because you don't need to save the file. You already have it. And then yeah, you get your data frame just by reading an existing file rather than generating one and then reading the one you generated. So this should actually be generated like that, and then that way we will know the difference between the one that was generated and the one that pre-exists. Yeah, and this since we're commenting out this line we only need for loading the one that was not generated. So yeah, because we already have events DF. So this is just to save the results of this. But once you have events DF defined, you don't need to pull it in. This line is purely for using a pre-generated file. All right, moving on with the reading. Our inventory has specific attributes per device, such as vendor, model, OS, version, hardware, revision, and role. We could add more attributes if we want to make the simulation more complex. The algorithm is capable of handling many different attributes. For the purposes of our analysis, we will focus on the PEs from Juniper, which are the devices we have generated events for. Therefore, we will filter the inventory to keep only those devices. All right, looks good to me. Problem resolution. We have to obtain two key results. And this is the big one too. So anytime you see this syntax P parentheses This is just not valid. There's no option for it. It's not like sometimes it would be a pipe key, sometimes it would be a division operator. No, a forward slash is just always incorrect. But problem resolution, we have to obtain two key results. The first result is P, the probability that combination of X leads to a failure. For all combinations of attributes, we call this absolute toxicity, and then the probability of combination X for all combinations. This will make it possible to obtain the probability that failure is a result of combination X. We will call this relative toxicity. And again, these are all typos. Please, please, please do not mistake that for division, as I did when I first saw these. Therefore, the first goal is to compute the probability of each attribute combination out of the different events failures we have. Now we make use of our parallelism with the shopping basket example, and we will use a very useful association rule mining algorithm called FP growth. It is not the only one, but it is quite fast and easy to use. I have used the Python library mlextend, which has a good implementation of this algorithm. There, and he didn't write his own implementation of the algorithm. He used the library, and he used an existing implementation of it. But first of all, we need to decide what attributes it makes sense to include in the analysis. This will be an important step. Adding more attributes that are not useful will only complicate the computation and take more time and resources. So it is better to evaluate what are real potential contributing factors. Is the software release a potentially contributing factor? Yes, definitely. Is the IP address of a device a contributing factor? Very unlikely. Why would the IP address be a cause? Furthermore, this is an attribute that will always be different per device. But if there was another attribute, such as the IP address of a Radius server that this device has configured, that could be a relevant factor, because the failure could be on such a Radius server, and you may want to identify this frequent pattern. In this sense, the following is the list of attributes added to the analysis. So target columns, there we go, list of attributes. Now for the purposes of the analysis, we are going to transform the fields column into a list of attributes where each attribute is a string composed by the attribute name : attribute value. This is to facilitate later some of the data manipulation, as we will use basically string matching techniques. There we go. Looks good to me. Looks good to me as well. Let's check in on the notebook and see if we can get this far in running the code. All right, so it's still going. The author did say that this would take a while. They recommended using the existing file, because this will just take too long to generate. We see it is taking very long to generate, perhaps too long. So let's make a deal, and yeah. So let's you know what? Let's say that this is long enough, and just get to this events data frame before continuing on. So now the events table has a new column called label_list, where the attributes have been transformed into a list of strings. All right, so advancing the bookmark, and we can see the events table printed out there. So, yep, this is just taking way too long. So what we're going to do is restart and clear all output. All right, and then we're going to comment out this line. comment out this line because we already have it saved. And now inventory won't take as long to generate. And then we're going to get events from the pre-saved file there. All right, so now let's go and run the cells. And that's commented out, so it won't do anything. So we should get here pretty quick. There's the regular warnings that we're used to seeing. There we go. We made it that far. Hopefully the import works. Import worked great. And now we've got the same data that we saw before. So we got to get all the way down now to this events data there. All right, that wasn't too far down. So here's the same thing. So let's continue. In the same process above, we have generated a dictionary that contains all the different attribute names, attribute value possibilities. In our case, there are 6 different possibilities. Larger scales could have hundreds or thousands. Now it is time to create our events basket, much like if it was a transactions basket. All right, events basket there. Looks good. This is how the events underscore basket looks like. We have 1 row per event, and the number of columns are all the possible individual values for each attribute. The table will contain a 1 in each position if such attribute value is associated to that event, or 0 otherwise. Now we have the data ready to run our fp-growth algorithm. Min support, there we go, looks good. When we run the above command, we are running the fp-growth association rule mining algorithm that will very efficiently compute all the possible combinations of attributes in the dataset, given a certain minimum support. If you remember from the theory, the support refers to the frequency of a certain combination. When we set a minimum value, in this case to 0.01, we are saying we want all combinations with a contribution higher than 1%. You may decide the threshold. The result table looks like the following. So frequent underscore FP, there we go, looks good. Okay, that looks good. This is only part of the table, but it is an ordered representation on how different factor combinations of 1 factor, 2 factors, 3 are contributing to the hardware error events. Some are very obvious. MX960, which is a form of Juniper, seems to be contributing to all, which is very clear. All devices are MX960, so that is not really news. Same thing happens to vendor Juniper. All devices under the analysis are Juniper, so it is not very useful to blame the vendor attribute as the reason for the problems. Then we see in third position a certain software release that is contributing to 74% of the problems. Is this bad? Is this release toxic? If 95% of the devices were running that release, then it would mean it is contributing less than its footprint. On the contrary, if you only had this release in 5% of the devices, then definitely this factor itself would be extremely toxic. This is the reason why we call this quantity the absolute toxicity. It gives us a perspective of absolute contribution to hardware errors, but it does not give you the full picture. With the table above, we have computed only half of the equation. P, the combination of the probability of the combination X leading to a failure, and remember this is a typo, just as much of a typo as if combination were spelled COMPINA. You know, it's that sort of typo. It's not a typo where there's any meaning or value in what the incorrect character is. There's no option for multiplication here. There's no option for addition. There's no option for subtraction. This is just completely irrelevant to this whole thing. It's meant to be a pipe character that stands for the probability of this part causing the probability of that. Nothing to do with mathematical operators at all. With the table above, we have computed only half of the equation for each combination x. Now let's compute the probability of combination x. The probability of a certain combination of factors can be extracted from the inventory itself. How frequent a certain combination is. So what we will do is, for each combination above, we will compute its normalized footprint in the inventory. That is its probability. All right, there we go. Looks good to me. Now we have expanded our table with two columns. Inventory footprint, this is effectively the probability of combination X. Relative toxicity, this is effectively the probability of failure being a result of combination X. This is an indicator of how badly such a combination behaves. If we observe the table, we can see various issues. Okay, so let's get to this table. Delete bookmark. So this is the frequent underscore FP table. So here's our events basket. I'm a bit lost. Okay, so now we're doing the for loop, and we got the events basket. So we need the table frequent underscore FP. That's good. I think, yeah. So we need to see the first 50 entries to get to the same cell as this one. Yep, so this is a slice. It's indexing. Looks like the table doesn't have 50 entries. It looks like we're only seeing 34. Oh, but I guess it does. Well, that's interesting. I wonder why there's only 34 showing up here. And there's no slider bar or anything. Don't get it. All right, so close to the top of the table, beyond the obvious entries, model vendor, we could see that release 21.3R1, which we saw earlier with an absolute toxicity of about 74.5%. It seems to have actually a relative toxicity lower than 1. It means it is contributing less than what its footprint represents. It is behaving well. On the contrary, we can see in row 5 for a particular hardware revision that while it contributes to about 33% of the hardware errors, its relative toxicity is 3.36. That is not positive. With a small footprint, it is generating way more errors than it deserves. Let's go a bit further down in the table. All right, so entry 30, which we have here. All right, let's see if we can find. So here's the absolute toxicity and the relative toxicity for entry 30. The relative toxicity is interesting. Is a 6. I wasn't expecting to see that. I was expecting to see another percentage under 1 value. Okay, so we can find in row 30 that a particular combination of software and hardware release is responsible for 21% of hardware errors. So this is the absolute. So yep, 21%. However, its relative toxicity is 631%, which means it is highly toxic. while the release of 21.3R1 was apparently behaving well as per above, in combination with the specific hardware revision, it results in a bad outcome, worse than that hardware revision alone, as we have seen as well. You know what this would be amazing for is drug combinations. This would be like a revolutionary thing if you could somehow use this for drug combinations. Okay, so bad outcome, worse than the hardware revision alone, as we have seen as well. Those results are very consistent with the way we have generated the data, and the algorithm has been able to capture very deterministically which are those factor combinations in the network that are driving, in this case, hardware errors. Of course, many factors are going to contribute to the hardware errors, and somehow we need to determine where we focus on given all the combinations that the algorithm exposes. One approach is to define certain thresholds to identify the concerning combinations. All right. Right, so now we have a threshold. If the absolute toxicity is more than 10%, then it's beyond the threshold. For relative toxicity, it has to be more than 200%. I don't know if that's a percent, but it has to be much higher. For example, any combination that contributes to 10% or more of the hardware errors and at the same time has a relative toxicity of 2 or more, it means it really disbehaves, should be of interest. We can therefore filter out our table and focus in what really matters. I really like this, and I feel like if you're on the job, you can do this. Like, you can absolutely do this. Like, yeah, you can absolutely do this. Just be careful. Don't tank your network. Don't flood the traffic. Don't do bad things. Do good things. All right, so let's see. So let's get down to the graph. I think this is where we're at. Oh no, so we're down here more. So we're at this graph, I think. Yeah, so now we set a threshold. Okay. And now we got this graph here. This graph gives us an area of interest. High absolute toxicity, greater than 10%, and high relative toxicity, greater than 2. Eventually, if something has a high relative toxicity, but it has a very low absolute toxicity, say only 1% of your network has such a combination, and you are not that concerned about the issues associated with it, you can possibly deprioritize and focus on the higher values. We can more programmatically extract the combinations of interest. All right, looks good to me. Looks good to me. So here's the results for that. Yep. Okay, so now we've got the relevant. Isn't this cool? Like, I can see this being useful for all sorts of different things. So I recommend it so far. If there's any use case to hone in on, definitely hone in on use case 6. Yeah. So what are the driving factors for problems in general? But in the network, yeah, like that's a good place to learn about that. But yeah, really powerful stuff. This is the first one I'd say where I was like, whoa, I can definitely see the potential of this. But you have to be very, very careful with the data, because you'd be like, oh, I see what's the problem is. My junipers are malfunctioning. It's like, well, you only have junipers in your network. Of course, all your problems are going to happen on junipers. All right, so given this, the hardware revision, we can see ending in 890, pops up quite a bit on here during our filters where we have high toxicity. Seems to be quite toxic, but especially in combination with the software release 21.3 R1. And another thing you can do is you can remove factors. Like, let's say that you only have this hardware revision in your network, then you can remove it as a factor. All the other entries we see here and combinations of those with others, vendor, model, etc., which do not change the result. We could improve the logic by eliminating those and make the result cleaner. Yeah, see what that's exactly what I just said. Yeah, if it doesn't change the result, it's all the same. Remove those factors and focus in on the ones that are making a difference. But be careful not to, if you have 99% of your network and 1% is not. You still got to look at that 1% because it could be a contributing factor to your issues. So if it's 100%, yeah, remove the factor. But even if it's 99.9%, you might want to leave it in there. If we go back to the way we had defined the event policies to force certain combinations to be toxic, the results are very consistent. The high probability of hardware fault events was associated with devices running such a combination of hardware and software. For the hardware revision alone, it is present in those devices, but also in devices that have a medium probability of event generation. So the algorithm has perceived certain toxicity, but lower than the combination. On the other hand, for the software release 21.3R1, we can see how it is present mostly in devices with a low probability of hardware faults. And the algorithm has detected that despite the fact that in combination with the specific hardware revision, it really results in toxic behavior. All right. So let's take a deeper dive into this. And this is the last cell, so it makes sense to dive into it pretty deeply. Now we do have we have to generate event policy here, so this might take a little bit of time. So, all right, so let's make some progress instead of just waiting for that and doing nothing. In our example, we have not used many different attributes, but you could run this in your network or cloud infrastructure in a wide variety of use cases. Particularly helpful where you have a good set of attributes characterizing entities for which you have events, customer calls, and attributes of those customers, Wi-Fi access issues, and attributes of the devices such as device type, OS version, etc. There are many possible use cases to apply these association rule mining techniques. They give us the opportunity to infer some level of causality for combinations that may not be obvious for the operations or engineering teams. So this is great. I do want to take a quick break here. Okay, so we do have this printing out now. So yeah, this is pretty cool. We get to the policy name. So we get hardware faults, and then we get the entity name, and so we can really narrow that down, and probability. So we got a 90% probability here. Yeah, pretty cool stuff. All right, so take a quick break. When I come back, we'll close out this use case. All right, so welcome back. You know what? So we've made it all the way through the notebook. We're very close to being done with the reading. So I do have a bit of time here, so let's close out UC 6, and then I want to add a note to it or a highlight or something to remind myself that this is the best one I've done so far, and that if I want to branch off and do some real world stuff with it, I should focus on what I learned here. All right, but the takeaways were the following main takeaways. The following are the main takeaways from this use case. Takeaway 1. Frequently, there is a lot of gold in our data. We just need to mine it. A technique used for shopping recommendation systems can be easily leveraged to identify toxic combinations. Ultimately, what we are trying to find are frequent patterns and how those patterns behave. And you can do that if you're a junior, if you're an intern, and you can this is gold here. This is good stuff. This is a good example of the importance of combining data sources. You may have monitoring systems that are collecting events or log messages. On the other hand, you have inventory systems that contain inventory data and some of those attributes that we have referred to. Merging the two data sources together, events and inventory, and cross-analyzing enabled us to bring new insights that otherwise would remain hidden. Identifying toxic combinations turns the data into something actionable. Such a combination needs to be addressed. Then, once it is addressed, the list of toxic combinations will still exist, but likely with combinations that are less toxic. You can progressively decide to address more, and in that process, improve the performance of your infrastructure progressively. Further work. There are multiple opportunities to evolve this use case. Try with new attributes and more complex combinations to evaluate how the algorithm can surface them. Also, provide a final list of results that eliminates those attributes that are redundant because they do not provide any meaningful information. Finally, I would suggest that you identify in your infrastructure new similar use cases where you could apply this approach and give them a try. All right, so we're going to move on to use case 7. Use case 7, what is the severity of this log message? So that's where the bookmark goes, but then I want to make a note at how awesome this is. So let's see here. Yeah, so I guess I'll highlight this. So I'm gonna add a note to it. I'm gonna say use case 6 is the best so far. It's based on proven and widely used recommendation algorithms to identify shopper behaviors. Can be implemented, can be experimented with safely, as it is only about analyzing data for insights, not about. Okay. Great for further exploration. All right, so there's my note. So let's go back to my bookmark. And yep, so this is use case 7. Let's take a final look at the notebook. Notebook is all good. So yeah, that's it for this video. Yeah, best use case so far. Can definitely apply this. Can even probably apply it in production. I mean, don't ruin anything, but yeah, if you can find some data to analyze, get really good with this. Go back through and actually understand what's happening in this code. Write your own code. Get this data out there. Spin up a Jupyter notebook. Yeah, it's really powerful stuff here that can be implemented in a non impactful way. So yeah, definitely recommend diving into this more. But for now, that's the end of use case 6. Stay tuned for another video where we start use case 7.